Okay, time to take a step back and discuss the relationship between hypothesis tests and confidence intervals. Now, you may not have noticed this, but hypothesis tests have a direct relationship with confidence intervals. In fact, they can be used to evaluate the same decision and would come to the same conclusion. So, if you use the same alpha, a confidence interval will include the hypothesized population mean when failing to reject the null hypothesis and won't include it when rejecting it. Let me show you how this works. Let's say that we're assuming that the mean employability scores of our accepted applicants before the program is 250, which would lead to these null and alternative hypotheses. Now, this is our hypothesized mean and sampling distribution, and this is the sample statistic. We got an average employability score of 239.9 from our sample of 95 students. If we were to set a significance level of 0.1, then this would be our confidence interval. Now remember, the size of the interval is determined by the confidence level, which is 1 minus alpha. So here's what this would tell us. A, since the sample doesn't cross into the rejection region, then we fail to reject a null hypothesis. For all we know, we're correct in assuming that the mean is 250. And the confidence interval includes the hypothesized population mean of 250. So even if we had done this instead of calculating a p-value, we'd come to the same conclusion. We have no reason to believe that the mean isn't 250 since it's part of our estimate. If we set a significance level of 30% though, or a confidence level of 70%, it's the same thing, then the sample statistic does fall into the rejection region, and the interval doesn't include the hypothesized population mean. So we would reject the null hypothesis. So not only does this show the relationship between confidence intervals and hypothesis tests, it also highlights the importance of being deliberate and thoughtful when setting a significance or confidence level, since just by changing it, you can come to different conclusions based on the same sample. And we're going to touch on that further in the next lecture. Alright, time to introduce the different types of hypothesis tests. There are 3 types of hypothesis tests that you can make. You can make a two-tailed test, which is what we've done already, or you can make a one-tailed test, which can be either to the left or to the right. Now, in a two-tailed test, the null hypothesis assumes that the population parameter, like the mean here, is equal to a certain value. So rejecting it implies that the mean isn't equal to that value. And if we visualize the sampling distribution, then the rejection region and the p-value consider the areas from both tails. Since in order to reject the null hypothesis of the mean being equal to something, then the sample can come from either extreme. Now the p-value formulas in Excel for these types of tests are the following. You can use t.dist as we have and use a negative test statistic to grab the cumulative probability of the area on the left and then just multiply it by 2 to get the total p-value. But if you have a positive test statistic like we did in the previous assignment, then you can either do 1 minus t.dist and then multiply by 2, like we did, or you can actually use the t.dist.2t function for two-tail, which we hadn't seen before, but will automatically return the area from both sides. Now, in a one-tailed test to the left, the null hypothesis assumes that the population parameter is greater than or equal to a certain value. So in order to reject it and accept the alternative hypothesis, then your sample needs to come from the left side of the sampling distribution and be less than the hypothesized mean, as you can see from the alternative hypothesis, in this case right here. And this makes sense because even if the sample comes all the way from the right side, then that just supports the fact that the mean is greater than or equal to the mean in the sampling distribution here. Now the p-value formula is straightforward since the cumulative probability starts from the left by default, so you can just use the t.dist function that we've covered. And finally, in a one-tailed to the right test, The null hypothesis assumes that the population parameter is less than or equal to a certain value. So it's the opposite of a one tail to the left test. Rejecting the null hypothesis here implies that the parameter is actually greater than that value. So here, since the area is on the right side, you can either take the 1 minus approach to the p-value, or you can use the t.dist.rt function, which stands for right tail, and then you're good to go. Alright, so I keep mentioning all of these accepted probabilities of error and the need for really thinking about the significance level for your tests. So let me put some clarity around all of that. There are two errors you can make in hypothesis tests, type 1 and type 2 errors. Granted, the names aren't very helpful, but here's what they mean. A type 1 error means that you have rejected a true null hypothesis. So your assumption was right all along, but your sample was improbable enough to cause you to declare it as wrong. And a type 2 error means that you failed to reject a false null hypothesis. So your assumption was wrong, but your sample didn't provide enough evidence for you to realize that, so you just kept assuming that it was right. Now, here's a good way to visualize this. If your null hypothesis is true, and you failed to reject it, then you came to the correct conclusion. Similarly, if your null hypothesis is false, and you rejected it, then you also came to the correct conclusion. But that still leaves us with two possibilities: rejecting a true null hypothesis, which is a type 1 error, and failing to reject a false null hypothesis, which is a type 2 error. So how do we control for this? Well, the significance level, which we know all about, is the probability of making a type 1 error. So the lower that you make it in your test, the less likely you are to make it. But inversely, the more likely you are to make a type 2 error. So there's always going to be a trade-off here. Fair enough. So which one is worse so I know how to protect myself against it? Well, it depends. Let's think about our soda example. What type of error is worse here? Well, rejecting a true null hypothesis means buying a new machine when you didn't need one. Admittedly, not great. But failing to reject a false null hypothesis means not buying a new machine when you did need one, which is probably worse in this case as it's potentially more costly. So to prioritize a type 1 error, you would use a higher significance level. Sure, maybe you switch machines prematurely now and then, but at least you're not waiting until it's too late. Let's look at another example though. Evaluating if an email you received is spam. The null hypothesis being that it isn't, as that's typically the default assumption. So what type of error is worse here? Is it type 1, which is screening an email that isn't spam, or type 2, getting a spam email in your inbox? I don't know about you, but I'd rather delete the occasional spam email myself than miss out on a potentially important email because the spam filter made a mistake. So here you want a low significance level to decrease the probability of getting a type 1 error. The important thing here though is that you'll never know what the right choice is with 100% certainty. That's statistics for you. So it's critical to think about how comfortable you are in making a type 1 or type 2 error in each hypothesis you test when setting the significance level. You might still make the wrong decision, but at least you minimize your chances of that happening. Alright, time for an Excel demo on a one-tail hypothesis test. So let's go through the link here and let's look at our question. We're assuming average employability scores of 300 from our graduates. We actually already tested this. But are they higher than 300 for placed graduates? Let's accept a 15% chance of type 1 error. Alright, so first things first, what type of hypothesis test are we doing here? We know it's not a two-tail test since we're using the word higher here. So is it a one-tailed test to the left or to the right. And the key in one-tailed tests is to look at the alternative hypothesis. So rejecting the null hypothesis here would imply that the population mean is in fact lower than our hypothesized mean. And rejecting it here would imply that the real population mean is higher than our hypothesized mean. So if we're assuming that they're equal to 300 from the start, this applies for both the null hypothesis is greater than or equal to here and less than or equal to here. But if we want to evaluate whether they are higher than that, then we need to use a one-tailed to the right test. That way, if the sample falls far enough to the right here, we'll be comfortable saying that it doesn't come from a population with this mean, but from one with a higher mean. So the null hypothesis is that the mean is less than or equal to, and in this case it's 300. Making the alternative hypothesis that the mean is greater than 300. Now let's move on to the significance level. We just learned that alpha is the probability of accepting a type 1 error, so it looks like this has already been defined for us. So alpha is 0.15, meaning that we're running a 15% risk of wrongly rejecting the null hypothesis, which means thinking that place graduates have employability scores higher than 300 when they actually don't. That's our type 1 error. And that's also not the end of the world, since shooting for high employability scores makes sense anyway. So a 15% chance of making that mistake, which isn't so bad, feels good to me. Now, I've already calculated the sample statistics here. We have 53 placed graduates with a mean employability score of 320.5 and a standard deviation of 86.49. So our sample mean is higher than our hypothesized mean, but is the difference enough to be significant? Well, let's test it and find out. The standard error is equal to our sample standard deviation divided by the square root of the sample size. The test statistic is the difference in our sample mean. Let me open the parentheses first. Difference in the sample mean minus our hypothesized mean divided by the standard error. So we get a test statistic of 1.73, so it is going to live somewhere on the right side here. Now let's just calculate its probability. And we can either use 1 minus t.dist, or let's try the t.dist.rt function. So t.dist.rt, we have our test statistic, and our degrees of freedom is going to be the sample size minus 1. Press enter, and we get a p-value of 0.045, which is lower than alpha, meaning that we can reject the null hypothesis and accept the alternative hypothesis. So if we look at the conclusion, let me change the font color here. Since p is less than alpha, we have sufficient evidence to prove that the average employability scores for placed graduates are greater than 300. And we should use this as a target, especially since we estimated that our program improves scores by at least 41 points on average, if you recall by our confidence interval on dependent samples. So it looks like we are on the right track towards getting higher placement rates for our future graduates.